Okay, so thank you very much everybody for coming. Thank you very much, Vosa, for doing all the interconnections so Stefan could be here today. And so today we have the honor of having Professor Stefan Voß from the University of Hamburg, and he'll be talking about exploiting erraticism in search by being less erratic. Thank you very much.
Thank you very much. It's a pleasure to be here. It's a pleasure to follow this invitation. And I would like to speak about something which is to some extent highly speculative, in the sense that probably all of you know on how to apply commercial software like Cplex, commercial solvers like Cplex or Gurobi. And the question is, do we do it right if we apply it? Sometimes what you realize is that you apply Cplex to your model on one computer, and then you go to a different computer and you get completely different results. Or you change from one version, 12.3 to 12.6, another version, and you believe you do it better, but you have a deteriorating result. Why is that? And there was a nice paper in Operations Research recently by Fischetti and Monacci, who developed some kind of ideas with respect to the initial conditions related to applying Cplex. And I would like to talk you through a couple of ideas that you could have related to erraticism, but not related to the initial conditions, but what you could do beyond. And that's related to modeling. So we would like to assume that we are modeling a problem, whatever it is, whether it's from logistics, whether it's from reliability engineering or other areas, and then let's see how we can reformulate the model in some sense, and we try to use common ideas from literature to do so, and maybe this allows us to improve the results, or in the worst case, to reduce the erraticism. So that's a little bit of the idea. I would like to motivate everything and give you results related to the multi-choice, multi-dimensional knapsack problem. That's a problem that we have seen recently in many papers, a 3-digit number of papers, and they have tried to find new best results and new best solutions all over time. And actually, to our surprise, we were able to improve some of them. And I will use that by means of a reformulation as a set partitioning problem. So it's a well-known combinatorial optimization problem. And then maybe we improve the results. Maybe not. There's erraticism. So that's the idea. And then the talk is finished, and this will be fast. But then I will go on, and I will talk you through a couple of other ideas, concepts, or applications where you can use the set partitioning problem or a generalized version of the set partitioning problem. And one of them is the dynamic worth allocation problem. And I will show you a math heuristic, which we call pop music, on solving that problem to some extent to optimality, maybe not, maybe heuristically, for this dynamic worth allocation problem by applying a generalized set partitioning problem. And then give you some kind of computation results, and at the end, if there's time, even talk you through another application in machine scheduling, where we have the same type of idea that we reformulate something as a set partitioning problem and see to which extent we can have better results and maybe even reduce the type of erraticism. So that's the outline for the next hour or so. If you have any questions in between, don't hesitate to ask. I would be happy to try to answer them, and then let's see how far we get. So this is, I call that VM, Virtual Environments for Advanced Modeling. So people in different areas have tried to model problems. And maybe in the 1970s and 1980s, we made a big mistake in operations research and saying, hey, if you are able to model the problem, we can solve it. Then we took ourselves a little back, invented meta-heuristics, and allowed people to work with heuristics and meta-heuristics to solve problems, maybe to some extent close to optimality, but not necessarily optimal. And that's where also the combination between mathematical programming and meta-heuristics, which we term math heuristics, is coming into play. So one of the nice things from those areas and from those times are put together in a phrase that especially Fischetti, a researcher from Italy who is quite famous in this area, called MIPIT. His idea was to make a mixed integer programming formulation for a problem, and then you can utilize that. That was the idea to MIPIT. But we have already done that in the 70s. Of course, now Cplex, Gurobi, and other pieces of software are much more advanced, and maybe it works. And also we have the possibility to link an exact approach with a heuristic approach. Maybe we have some kind of partial optimization where we look into some specific area of our solution space. We fix everything around and try to solve the problem if it is small enough to optimality and use that on a larger scale. So that's what we want to do. And my intention for this talk is just to give you a little food for thought. So as I said, it's somewhat speculative. We give you some kind of food for thought, and you try to use that later on in your research maybe. And there's other types of papers which are going along in the same spirit. You might have heard about the feasibility pump. You might have heard about local branching, RINS, the corridor method. All these methods are trying to do similar things in a sense that they try to link mathematical programming and heuristics, or mathematical programming and meta-heuristics. And even if you assume that in Cplex or in Gurobi you have an exact approach, there's a lot of heuristics inside, because you have to add cuts to make your problem being solved in an efficient way. But the way they define the cuts, the sequence in which they define the cuts, maybe at random, or at least heuristic. So that's where the erraticism comes from. You have a different computer, you have a different memory, and then the constraints, the Gomori cuts, or whatever you have, are given to your model in a different way. And that results in different solutions eventually. So that's what we try to look at. So what you see on this slide on the right-hand side is just a classical way to represent your problem. You have a model, you have cutting planes, you try to cut away some parts of the solution space without losing optimality, but those cuts are generated, and you have tons of them. But you can only select a few out of those tons. And that's what we need to look at. And maybe there's a good way, in the old-fashioned way to say that, we had an algorithm to have a separation routine to put the cuts and give it to the model, if you solve it with respect to the LP relaxation, the linear programming relaxation. So now, if we no longer put a controlled algorithm to give the constraints to Cplex, because we let Cplex do that, then maybe we are in bad shape. And that's what we look at that. So every solver, whether it's Cplex, Gurobi, or others, has its own recipe to handle those constraints. And what we try to do is we try to measure what can be achieved by a single cut to be added to a given mathematical programming formulation, mixed integer programming formulation, in the sense of MIPIT. And what most of us do, we use Cplex as a black box. But I would like to give something to Cplex that this black box is working a little better than before. And Fischetti and Monacci have worked on that and have looked into the sensitivity of the initial conditions. The initial conditions of what you provide to Cplex. And that's what we would like to do. And there's many other areas and methods where we can borrow ideas from. So for vector machines, maybe greedy randomized adaptive search procedures grasped from the meta-heuristics community, and so on. So there's a lot to do and to copy from those areas. So let's try to be specific. I would like to work you a little bit through the multi-choice, multi-dimensional knapsack problem. And we have a mathematical programming formulation for that. So you probably know the knapsack problem. This is a slightly generalized version. We are given a set of items. We have to partition them into n disjoint classes. And each class has a certain number Ri of items. And each item has some kind of profit. Profit value Cij. And it requires a certain amount of a resource. And then the idea is that the capacities of these resources are somewhat limited or constrained. And then we try to pick exactly one item out of each class, trying to ensure that the resource constraints are observed and maximizing the objective. So that's what we do here. We maximize the objective, Cij times Xij, when Xij is the variable to choose a certain set and its element. And then we have to observe those capacity constraints. So we have the restrictions with respect to our subsets, and that's what we do. And we have a weight vector for that. Wij is going to show us to which extent, if we choose something, some element, some item from a subset, and we have the kth constraint, then Wij gives us the consumption, and the sum of all that needs to be limited by means of the capacity constraint. And then we have one constraint ensuring that we actually take one item out of each set, exactly one item out of each set, and we have the binary constraints. So this is a classical problem. Many people have worked about that, and we have seen, as I said, a 3-digit number of papers on this. And we try now to solve that. Why would we be interested in doing that? Because there's lots of applications of this type of problem. The reason why we came into that was that we reformulated a reliability engineering problem coming from redundancy allocation as such a multi-choice, multi-dimensional knapsack problem. And for that problem, the reformulation as a multi-choice, multi-dimensional knapsack problem actually allowed us to kill all the results in literature. So there were lots of benchmark instances which were not solved to optimality. We reformulated it, and then we defined a branch and cut algorithm, and alternatively a dynamic programming algorithm. And with them, we could solve all of those benchmark instances that people in literature had not been able to solve beforehand to optimality. Now, where's our innovation? Maybe there's even no innovation because that type of transformation was almost known from the 1980s, but nobody applied it now. There was still a little trick, so we had some extra transformation between discrete and binary, but then we were able to solve all of those instances to optimality. Now, try to reformulate that as a set partitioning problem. So the idea is if we reformulate this multi-choice, multi-dimensional knapsack problem as a set partitioning problem, then we might be able to have a different formulation. Maybe even in the same sort of dimension, in the sense that we have now a linear number of constraints. So we have a certain number of columns, but in a quadratic dimension, which means that literally we are ending up with respect to the same type of formulation. We just give the constraints in a different way to the solver if we apply a commercial solver. So the idea is that we have a set of columns which is denoted by omega, and those have all those Ri elements summed over all those I. And then we define two matrices, A and B, both having omega, the cardinality of omega I columns. And the matrix A contains n rows, one for each class, and a 1 AI omega, if and only if column omega represents an assignment of item I. And each column of A contains exactly one non-zero element, and then the other matrix can be defined with m rows, and again the cardinality of omega columns, where each row represents the resource requirement of an item. And then we can just reformulate the problem as you see on the slide in the lower part. So that's a simple reformulation. Now, once we have done that, we give it to Cplex. Let's see what happens. So this is interesting. We did that. This was done together with somebody from the University of La Laguna in Tenerife, Canary Islands, Eduardo Lala. And we looked into the hardest instances that have not been solved provenly to optimality in literature. And we applied MMKP, which is the classical formulation. And we applied the reformulation, which I call SPMMKP. And we applied that to some benchmark instances. We gave it to Cplex, didn't worry about anything, let it run for a certain time, 7,200 seconds, and looked at the results. And we were really astonished what happened. If you look at the columns with respect to OBG, objective function value, then you see one highlighted value, which actually gives us a new best solution over everything that we found in literature. That was astonishing. And also, if you look at the number of best solutions, then the reformulation actually gave us something better. This was, to some extent, astonishing. And also, if you look at the time, then in some cases, we were able to reduce the time a lot, but not consistently. As I said, it's some sort of erraticism that we try to explore, and we just try to play around and learn something. So those results are now just for learning purposes. We just try to see something. Now, what would you do next? OK, try a different solver. So try Gurobi, or whatever your favorite solver would be. Or give it more time, or you name it. So there's lots of options what you could do. And you don't have to look at the numbers. There's one number which is highlighted in red, which is just looking into some other benchmark instances. And the same thing happened. We found a new best solution. And then we looked into another set of benchmark instances, and we were really astonished. Now, this was even more erraticism, because we found a new best solution with respect to one of those, I never know how to spell that, Shojai benchmark instances. And we found a new best solution. But then we saw we actually found two new best solutions with the old formulation. So, any conclusion from that? We don't know. So that's quite erratic. But still, if you look at the number of best solutions, which is given in the last row, then we are improving a little bit. So we have not only 5, but 7 best solutions within that test. So is that encouraging or not? Now, the question was whether we could go on and maybe try to improve a little bit the situation here. And among all those options that I gave you, which one would you like to choose? We chose Gurobi. So now we did the same thing with Gurobi, and we were even more astonished, because we found a couple of more new best solutions for that set of benchmark instances. So that was quite interesting. So what should we do? OK, put it together in a paper and send it away. But then the referees would probably say, hey, where's your innovation? You just used Cplex, and you just had a formulation. And then we would say, we have a reformulation. And then the referees would say, but your reformulation has the same dimensions, so where's the innovation? And people in public transport have used set partitioning models all around, and other areas, it's the same. And my answer would be, yes, but. So let's try to use that in different areas. Maybe we can learn something from that. So just going into a different area, what do you do in metaheuristics? Usually what you do in metaheuristics, you have a problem. Maybe you model the problem. You solve it by means of a metaheuristic. You define, maybe by means of a local search approach, a neighborhood, and then you try to explore the neighborhood as efficiently as possible. That's what people do. We call that a move-based neighborhood. So we define the neighborhood, and we find an efficient method for its exploration. So you might remember for the traveling salesman problem, you have a couple of nodes, you have distances between those nodes, and then you have a feasible solution by some method, and you try to improve that by means of a true optimal exchange. You take two edges off, put two edges in, and you compare the objective function values of those two solutions. The next step is, hey, I could be more clever. I just calculate only the difference of those edge values of those two that I take off and those two that I put in. That's a slightly more efficient calculation. And then you can come up with more ideas to do that efficiently. Okay, good. So that's what we know. A different way to look at it, and you might have seen that for very large-scale neighborhood search or adaptive neighborhood search or RINS or limited discrepancy search, is a method-based neighborhood. I assume that I have a method to solve the problem, if it is small enough. Let's assume I can solve the problem to optimality if it's this small. That's perfect. Then maybe I have an initial feasible solution for solving the problem, and I make the neighborhood this big. Because then I can solve the problem to optimality. And maybe I try to do that. So that's a completely, maybe not completely, but somewhat different concept. If the assumed method is an exact approach, like dynamic programming or branch and cut, and on top I have a guiding process, which is a meta-heuristic, then I'm entering the area of math heuristics, combining mathematical programming with meta. So let's try to do that. So I would like to do that for an application. The application is in maritime shipping. I assume that I have large vessels going around the world, and they are calling at ports, specifically at container terminals. And those container terminals, to some extent, are open systems of material flow with the water side and the land side. And at the water side, we have to call with the vessels or with the ships. But of course, I have different places for those vessels to go. So if you allow me to just move for a second. So you have those options to let the vessels come in, and then they can call at different parts of the port, at different berths. So we call each of those places along the port, we call that a berth. And each berth might have different types of equipment, infrastructure, like cranes that are serving the vessel, taking containers off or putting containers in, dispatching or loading, or unloading and loading. So different berth places have different properties. And that means I have an optimization problem where I can try to have a better place for the vessel or a worse place. And the berth allocation problem that we are trying to look at consists of determining a berthing time, a berthing position at the quay or at the water side for each vessel to be served within a given planning horizon. So that's the overall idea. We try to solve that type of problem. And there's a whole bunch of literature on that. I don't want to go too much into detail, but trying to use a little bit of that literature and trying to solve that. So what we have is a dynamic berth allocation problem where data becomes available over time, which means vessels are coming over time. They are not all there at time 0, but they have certain time windows. And they will arrive at the beginning of a time window, and they need to be served until the end of the time window. So I have an estimated time of arrival, and I have an estimated time of sail or departure time for all those vessels. I have a handling time depending on the assigned berth and the equipment or infrastructure which is available at that specific berth, different types of cranes, etc. And each vessel or each ship has a wait priority value. And that's maybe changing because I like some shipping company more, or they pay more, and then I value them slightly higher. And I have a certain number of berths. Availability time windows with respect to those berths, they are open or closed, and forbidden berths for some vessels. There are different types of ways to say that, but one way is to have the depth of the vessel, so I might need some certain depth. If the berth is not providing that, the vessel is not allowed to go there. Now, is this a nice problem? What should we do with this problem? We want to solve it, but how to do that? Do you have an idea? MIP it, perfect. And which type of MIP should we try to use? A set partitioning problem, right? At least according to what I said in the beginning, that would be no surprise if I would do it like that. So the idea is I would like to find a mathematical programming formulation which is using the concept of set partitioning. So I formulate a generalized set partitioning problem, and I try to solve the problem. So that's what we try to do. Let me try to visualize a little bit what we have in this type of problem. So in this picture, we assume that we have 3 different berths. From bottom to top, the first berth, which has vessel or ship number 1. The second one, the second berth, which has ships number 2, 4, and 6. And the third berth, which has ships number 3 and 5. And within the picture, I have given those priority values. They might be different, they might be similar, or the same. And then I have some shaded areas, like for berth number 1, I have on the left-hand side and on the right-hand side, for the lowest of those berths, a shaded area, which means that it's forbidden to use. Below that graph, I have those lines, which are according to the time line. So I have the time window for the different types of vessels. The time window for ship number 1, for instance, says I'm allowed to come in at time 4, and I need to stay at most 10 time units, and I need to leave at the latest at time 14. And what you can also see on the right-hand side of the picture are the ship handling times depending on the berth. So in this case, I have 3 different berths, and then I have 6 vessels or ships. And the numbers in this small matrix give me all the ship handling times depending on the specific berths. So that's a certain way to think of the problem. There's a question related to what is the priority. The priority value is giving you some priority of the specific vessel. So maybe the shipping company is telling me that this needs to be handled with a certain priority. Maybe it is a little late. I need to bring it back on schedule. And then I need to give it an exceptional type of handling.
You don't have to pack all the ships in the first one?
No. The question is whether I have to put all of the ships at the berth or not. Yes, I have to put all of them. If the problem is, in a sense, non-feasible, I make it feasible by means of adding an artificial berth, which has an infinite length. So I assume that I always have a feasible solution. And if there's no feasible solution, I make it feasible. And for all the vessels, I have a certain priority. So if you look at specific applications, Singapore is an example for that. So if you are in the Bay of Singapore or in front of the port, you see lots of vessels waiting. And they might have different priorities, and some vessels are going in earlier and others have to wait longer. That's related to the priorities and also according to the contracts that they have with those terminals. And maybe your contract says, whenever I'm coming, just push everybody else away. Wasn't that the case for those cruise liners in Valparaiso? So if they are coming, everybody else has to go. Even if you are an important container vessel, the cruise liner comes, it has priority over your vessel. And that is reflected in those numbers. Does that answer the question? Okay. So that's the idea. And this picture is the same as before. It just adds a little bit in the sense that we have a solution structure for this problem. So now what I do in the lower part of the picture is I just put the vessels from the specific berth, like berth number 1 has 1 vessel, and I put those priority values delineated by 0, then the next vessels with respect to their priorities delineated by 0, and so on. I could also use the numbers of the vessels that would make it unique. It's heuristicity, so that's why I use that type of solution structure. The idea with respect to the objective function value is that we try to minimize the time in port for the vessels, or the weighted service time for all the vessels. So we want to determine the berthing position and berthing time for those vessels arriving at the port. Now we make it dynamic. They arrive over time, such that the total service time for all the vessels is minimized. And I incorporate the weights with respect to those specific vessels. So it's the weighted service time. There's different types of objectives that you could think about in maritime shipping, which is trying to minimize the time in port. That's maybe the first most important key performance indicator. Maybe the second is the cost for the shipping companies, which is not really reflected directly, but indirectly over the weight. So maybe a shipping company which is paying more gets a higher weight than one which is not paying as much. And the third thing is probably reliability. Reliability could mean, according to weather conditions, the vessel is coming late, but then maybe I should use, as a terminal operator, more equipment to actually bring it back to schedule. So just to reduce the time so that it can still leave within the intended time window. Yes, there's a fixed time horizon so that I know where the vessels are coming. And there's lots of imponderabilities that I could take into account. Like if I would show you a picture from Hamburg, my hometown, so we are at a river. And there's a more than 100-kilometer long way from the open sea to the port. And the largest vessels, because of the depth, cannot go all the times into the port. They have to sail on the high tide. So they are literally coming into the port with the wave, which gives me a very tight time window. And of course, they also need to go out. And they have to take into account speed constraints. And maybe the speed is not the same, the constraint from the port authority, the speed constraint is not the same as what the vessel might need for going out. So maybe for going out, I need to be slightly in front of the wave, and then the wave is going to catch up. So that at the critical places, I'm actually passing through on the high tide, on the wave. But there's even more constraints, because not at all places in the river, all vessels can pass each other. So that's nice constraints, nice problems. So I only want to do this kind of academic thing, and I still don't want to solve the real problem. We are solving the real problem, but this is an academic exercise now, because I want to apply this set partitioning problem. No, I'm joking. That's it. But it's an academic exercise. The real world looks a little more nasty. Now, remember this one? I want to apply a method-based neighborhood. So what I want to do, I want to apply pop music. So pop music is the following. I assume that I have a feasible solution, and I fix a certain number of variables and leave a certain number of variables open. In a sense, I do some kind of partial optimization. While I fix some variables, I leave some others open, and I re-optimize them, maybe by means of an exact approach. So I do some kind of partial optimization. That's the POP. And it's a meta-heuristic, that's the M, under U special S intensification I conditions, C. So I am fixing all the variables around, which is, in a sense, giving me some kind of intensification conditions. So while I have fixed that, I'm intensifying the search around the part that I leave open and re-optimize that. That's my pop music approach. That's the classical math heuristic approach. while the math-heuristic phrase is already known since 2008, 7. We tried to promote it since 2006, and in, I think, 2008, it became actually successful. So that's, just give it a handy name. Trying to be more specific. What we have here is that we assume that we have a problem where we have different parts of the problem, and those parts are put together in a sense that I have a subproblem. So one part, and then maybe 1, 2, 3, 4 neighboring parts make a subproblem. In this case, if you look at the right-hand upper side, you have something like a location-allocation problem. And if you have a location on the left-hand side of that figure, then you probably do not assign a customer from the right-hand side and just move everything through the whole picture. You probably choose a location more to the right for that specific customer on the right-hand side. So in that sense, what we do, we try to combine those parts. So let's assume that we have a small part as part of a subproblem. We have a couple of parts that we put together to build a subproblem, and we fix everything else. Then we have a solution, possibly even an optimal solution, for that subproblem, assuming that all the other subproblems are fixed. Then we fix this subproblem, or these parts, and release others and trying to re-optimize them. So in that sense, we assume that we have a feasible solution. We have an initial feasible solution. We decompose that one into parts. We optimize a subproblem or a portion which consists of several parts. And there's one parameter which tells me R, the number of parts that I'm trying to optimize together. But the nice thing with respect to our birth allocation problem, it has a natural definition of parts. One birth, one part. So if I know that I can solve a birth allocation problem with 3 births, then I just choose those 3 births and solve that problem to optimality, assuming that maybe the number of ships that have to be assigned to those births are restricted. But I can do that in the sense that I take a feasible solution, and I already have an assignment of a certain number of vessels or ships to those 3 berths, and then I re-optimize, which could mean one vessel goes from one berth to another berth, or one vessel is just moved in time in the specific assignment that I have, and then I have a new solution. And then I go and re-optimize another set of 3 berths together. And if I can solve a problem with 4 berths, then my R is going to be increased. And I can do that. So that's what we do. We assume that we have an initial feasible solution, even if I don't like randomness, but in this case, I just use a random greedy method to find an initial feasible solution. So I choose the vessels and assign them to the berth in random order, and each one gets the best place which is still available among those that I have chosen. Then I assume the partitioning or decomposition with respect to the way to represent the problem, as I mentioned earlier. That defines the different parts related to the specific berth. So in this case, we have 3 berths, and they make a set of optimized parts. So I take a part, and I try to re-optimize it. I try to optimize it. And if I have done that, and if I have been successful, I put it back. And there's 2 options. Either saying that the set of optimized parts is still empty, and I randomly choose the next one, or I memorize what I have done, and I don't choose the same one again. So this makes 2 different versions of our pop music approach. So this is what I do literally next. So I define a subproblem based on my approach, which is maybe an exact approach for a birth allocation problem, assuming that it is small enough. So I build those subproblems, and then I solve them by means of a generalized set partitioning problem, which is given as GSPP in this red area. So I have a mathematical programming formulation as a set partitioning problem or generalized set partitioning problem in the same way as I showed you before for the multi-choice, multi-dimensional knapsack problem. And I solve that to optimality. And the distinction between the two pop music approaches is whether I just keep track with the memory on those optimized parts or not. But that's even not so important. Now, just for the sake of completeness, this would be our generalized set partitioning problem. So I assume that I have the same type of formulation that we had before, and I have the set of columns denoted by omega. Matrix A, as before, contains a row for each vessel, and matrix B contains a row per birth and time position. And with that, I have a maybe nice, maybe not so nice, but I have a reformulation of the problem, and I can use that. And to be honest, I did not invent that formulation. That was given in literature. But I reused that formulation in the frame of the pop music approach. So let's see whether we are somewhat successful. So the outline is that the pop music approach assumes a given solution, which is in the middle box on the right-hand lower side. I define the solution parts based on that solution. And then I go to the solver. And I define a subproblem, which is small enough, based on the parameter r, which means I have a reduced problem instance, which is going to be solved by means of that generalized set partitioning problem. And then I give it back. I have a new solution, and I could go on. The trick that we had in branch and cut approaches, exact approaches in the past, was the following. We defined the separation routine. What's the trick here? The trick here is the sequence of the parts that I take, together with the parameter r. But I just want to have some sort of proof of concept. I just pick them at random. Now, if you want to do some paper, just work on not doing it randomly, but give it a controlled way to choose those parts. Together with an autocatalytic way or autoadaptive way, defining R. And maybe, I will have that as a conclusion later, maybe even looking into those parameters of Cplex that you could influence. There's tons of parameters that you could influence. 200 are important, the rest is not. So just choose a couple of those parameters in Cplex and play around with that. Probably you don't like to do that because it takes time and maybe does not provide too good results. Now, trying to be academic, we try to win the horse race. So we take some benchmark instances from the literature. There's some instances from Cordeau et al. And from Lalla et al. And we compare with some algorithms, not so important right now, different types of computers, and OK. So we have the generalized set partitioning problem for smaller instances up to 40 vessels and 5 births. We can solve them to optimality and need a certain time for that. With the different pop music approaches, I just take the average result over trying all different values of r equal to 1, 2, 3, and 4. In all cases, we find the optimal solution or the best known solution in the other cases when we have larger instances. And we need some time for that. And among all those competitive algorithms that I mentioned on the slide before, the taboo search with plus path relinking, P2S plus PR, has some results. And the gap that we provide is occasionally giving us a value larger than 0, which means that we are better than those best known solutions from literature. So for an academic paper, we won the horse race. So in that sense that we are able to improve those results, of course, we need to put much more time into that. But that should be OK. Now, I didn't exploit any erraticism right now. I just gave it to Cplex. Now, what should be the next step, and I should not bore you too much with that, but the next step could be to use the reformulation of the multi-choice, multi-dimensional knapsack idea and put that into this string and see what happens in that respect. But in the interest of time, I would just like to conclude preliminarily and say, look, we have done this dynamic birth allocation problem. We have tried to solve it with pop music. We have used the idea of reformulating, and this idea is somewhat based on our experiences that we had with this erraticism. With respect to the erraticism, we have seen that maybe using some sort of reformulation as a set partitioning problem may be beneficial, and we have done that. And if we want to be really helpful for practice and putting that into a decision support system, then we should do the following. We should be autocatalytic or auto-adaptive. The user should not play around with parameters. So in that sense, we would assume that the choice of the parameter R and the choice of the parameters for C-flex or Groby should be done in an automatic way. And there's literature in actually providing us algorithms on doing that. And the next step for this local area that we have should be to apply those algorithms. But the title of my talk was different. So I should go back to the erraticism a little bit. And let me show you something that I really like, because we are currently working on the port of Hamburg. I don't have a picture of that. But we're also working with respect to the old part of the port of Shanghai. So what you see here is on the left-hand side of the picture is the old I³O port terminals. And if you go to Google Maps, can we go to Google Maps? We should not do that. But if you would go to Google Maps, then you would see that there's some kind of sandbanks and islands in front of those container terminals. And our decision support system now tries to find a way whether those vessels have to go north or south of the sandbanks. They have to take into account the water depth. They have to take into account the high tide and the low tide. And they have to take into account the speed that they can take. And they have to go in two directions, into the I³O port area, which goes from right to left, or out of that area, which goes from left to right. And that is a nice optimization problem. We call that the waterway scheduling problem, and that's related to this Yangtze estuary. And this is very similar to what we have in Hamburg. Just that in Hamburg, there's only one way, and the constraints are somewhat more binding. But literally, that's a nice problem. So now we try to solve that in a real fashion and trying to apply what we just mentioned today in that setting. But I don't want to provide the results right now. If somebody's interested to get a paper on that, I could send that. Now, let's try to go back to be academic. So I would like to do the same type of thing again. What was the idea? We wanted to talk about the erraticism. So I use some type of problem which is now taken from machine scheduling. So I have a problem with identical parallel machines. I have a certain number of jobs that I have to assign to those machines, trying to minimize the mean completion time. So this time I mentioned the objective first. And with respect to that, I have to take into account one additional side effect, which means that every job needs to be started in a certain time frame. Because maybe I set up a certain temperature for the machine, or I set up some tools, and that setup only works for a certain time frame. If I do not start the job in that time frame, then I need to pay some kind of extra time. That's what we call a step deteriorating function. So I first have the idea that I have a processing time. I have a starting time for each job in a solution. If the job is starting within the allowed time, not going into the deterioration, then it has a certain processing time. If it goes into deterioration because it starts too late, then I have some kind of extra time that I have to pay. So if you look at the picture, we have a certain number of jobs. If you go from top to bottom, then the first machine has job number J1, firstly, and then job number J2. And what is visualized here, without giving you the detailed data, is that job J2 is starting too late, so I need to have some extra time, which is the shaded area behind job 2. And maybe job 10 is also starting a little late, so I have the shaded extra time. And then job 12 is also starting a little late, so I have the shaded extra time. And my objective is to minimize the mean completion time, or the sum of all the completion times.
The extra time is a function of the starting time, or is the extent within days, or how do you...
The question is whether the extra time is a function of the starting time, or that's what we actually do. We just have a specific value in this simple case, because that's what we find in literature, and we want to just compare ourselves with those people in literature. But any function is feasible in the sense that if it's defined by the practitioner, then we should care about that. But right now, we just have one step. And you could have several steps based on time dependencies with respect to how late you are or how much you go over the duration. In the sense of the temperature example that I mentioned, if the temperature goes gradually down, then I need to reheat a little more. And in that sense, I might have more steps. I assume that I have only one step. So that's what you see, and the same thing on different machines. Some jobs are started in time so that I don't have some extra time. Some jobs are not starting in time, so I have to incorporate some kind of extra time. That's the idea with respect to this type of problem. So it's a simple case, 12 jobs, 4 machines. And again, the question, what should we do? Now, we formulate that problem as a set partitioning problem. So we did that. There is one reference from the literature, and they already mapped the problem. That's the columns MIPC. So we have, for small instances, with the number of jobs, 6, 8, and 10, and the number of machines between 2 and 3. By the way, what's happening if you are a researcher working your whole life on 2 machine scheduling problems, and you enter the midlife crisis? You move over to 3 machine scheduling problems. That's what we do. And this mathematical programming formulation from literature has been applied. Objective function values have been determined. And we have applied the standard T-flag solver. The time is exploding for the largest instances. Now, we have reformulated that as 2 different versions of a set partitioning type problem. I don't want to go too much into detail what we did there. The only thing is that we said, OK, just reformulate it as a set partitioning problem in the same spirit as we have done it before. That's the first formulation. And the second one applies a couple of logical tests that we have been obtained while we were looking at the specific step function that we had, taking into account that we have only one additional step. And then there's maybe some logical observations to reduce the number of columns in that matrix. So in that sense, we have the results that we get for our formulations, which are actually, of course, the same with respect to the objective function values, but the time is much faster. And then we also have a comparison with respect to a simple greedy mechanism and a variable neighborhood search that we have seen from literature. So for those small instances, the variable neighborhood search is giving us those optimal solutions. And the greedy method sometimes has some kind of deviation from those optimal solutions. Two things. The first thing is that probably we can take our approach of reformulating and solve bigger problem instances. And secondly, if the logical tests allow us to give the constraints in a different way, we may even be faster. Or, and that was the good result of this research, what we did here is looking into larger problem instances. And while the original formulation was not able to solve any of those problem instances to optimality, our formulations were able to do that. So the first columns here give us the instance size, 20, 40, 60. with a couple of machines up to 10. And the first reformulation as a set partitioning problem is giving us optimal solutions up to 40 and uses a reasonable amount of time. Those are randomly generated instances. There's a benchmark set of instances from the literature. So they have some sort of uniform distribution with respect to processing times and extra processing times for the deterioration values and so on. So we just use those data that were provided from the literature. But the interesting observation is if we just have those logical tests to reduce the columns or give some constraints later to the solver and some others earlier, then we can even go one dimension up and solve problems to optimality with size 60. Question? The question is, what is the general lessons to be learned or the general principle in respect to the formulation that we have? And the first thing is that if you have a mathematical programming formulation of a problem, then you might win or you might lose. And in many cases, a set partitioning-based formulation may win because it incorporates a lot of structure into the type of formulation. You have a matrix with lots of zeros and ones, and the matrix also has a very nice structure. So depending on the specific type of problem, you might have some sort of block structure. And those blocks are allowing you to have zeros outside and ones inside. And utilizing that block structure in a commercial solver may be very beneficial. So that's the first lesson that you could learn from that. The second lesson is if you give the constraints in a different way, then maybe you utilize parts of that block structure in a certain way. And then if you cannot do anything more with that specific block, you go to the next one, rather than overutilizing that specific block. And that could be done by means of using the reformulation within the reformulation. I hope this answers the question a little bit. So the idea is that I have a reformulation as a set partitioning problem, which can be beneficial in many areas. We also see that it is beneficial in this area. And then, depending on the number of cuts that a commercial solver like Cplex or Gurobi is defining, it might get, in a sense, and now Bob Bixby would kill me if I say that, but he was the inventor of Cplex. In a sense, you give a certain structure to the solver, and they choose those cuts, those Gomori cuts, in a certain way. But if I'm overdoing that, then I'm stuck in a certain area, while another cut in a different area might be much more beneficial. And that new reformulation within the set partitioning area. So set partitioning reformulated as set partitioning in the same dimension, but reversing the order, having some kind of logical test and saying, okay, I don't need these columns now, or I don't need these rows now. Just get rid of them and put them below, and don't use them now. That allows me maybe to go and have other types of cuts. And they might turn out to be beneficial, allowing me to solve the problem faster. Or even going into the case that I have some kind of non-existing memory problems. Very often, solving a problem with respect to those commercial solvers ends up in being troublesome related to the memory requirements with my computer. And maybe because I'm just moving to a different area where I utilize different blocks of the matrix, I might not run into those memory problems. No, both formulations have that structure, but I utilize that in a different way. So it's the same type of formulation, it's the same type of structure, but I'm just, based on some kind of logical observations, I'm just removing something from here and put it there. From the top somewhere and put it below. And that actually allows me to solve problems in a much better way. And if I compare with those algorithms from literature, then those are heuristics or meta-heuristics, then I see that for some of the instances, I actually find the optimal solution, and they had never been solved to optimality before. And also, the authors of those algorithms might be happy with our results, because we can actually show that their results, not for this heuristic, but for the VNS and the VNS together with that heuristic, are turning out quite efficient. So the deviation, the gaps that we have here, are actually quite low. So actually, our research also proves that this VNS plus the initial method are providing very good quality results. And of course, much lower times than we actually needed. Now, if I would summarize that again, what Fischetti and Monacci have done, they have investigated the erraticism, and they have looked into the variability associated to the initial conditions. What does that mean? They have looked at the situation where you just have a certain formulation of the problem, so you mip the problem, and then you looked at the initial conditions. What do you provide to the solution method up front? And what we try to utilize is trying to have a different formulation where even throughout the search process and the optimization process, all the constraints that go into the solver, because you still have to define those cuts, are given in a slightly different way. So we aim to investigate the effect of handling different formulations of the same dimensions for the same problem. As an academic, we might have difficulties to argue why we need those formulations if we just look at the formulations. But if we look at the results that we have here, then we actually have quite good results and quite consistent reasoning that if we put that into a commercial solver at a different pace, we might be successful. What is missing is a definite lesson that we have learned, so that we give you a recipe on how to do that. We have done that for specific types of problems, but we have not given you a recipe. That's what we need to work on for the future. In that sense, I hope I gave you a little food for thought, as I intended in the beginning. Just make some kind of advertising at the end. There's a nice conference in September in Holland, International Conference on Computational Logistics. So if you'd like to go there, and maybe paper submission is over, but if you want to have an extended abstract submitted, that could still go. Thank you very much. And I'm open for additional questions.